In this video, I will add movement to the food objects to make the game more engaging. Furthermore, I will ensure that the food objects avoid colliding with each other. Additionally, I will create an escape response for the food objects from the worm. Lastly, I will program the letter-free food objects to chase after the worm and eat its last body part. I will refer to these food objects as monsters for simplicity. To achieve the first goal, we added two fields to the food struct. We will discuss the field T0 later. Let's examine the default values of the fields. In fact, the last field does not have a default value, so it is not appropriate to use the derive attribute here. Instead, we can manually implement the default trait. The speed is set to 2.0. All the constants are defined in the consts.rs file. For more information about the instant struct, please refer to the link provided. Now, let's consider how we move the food objects. We can calculate the new x position based on the speed component along the x-axis, as well as the new y position. When a food object touches the border, it bounces back and is also pushed away from the border by a force. For example, if a food object crosses the left border, it is bounced back and a force is applied to push it along the x-axis. The same happens if the food crosses the right border. If the food stays between these two borders, no action is taken. Please pause the video to review the code for handling the y-axis boundary collision. Due to changes in orientation, the paint method needs to be modified. The position of the monster is defined as the center of the head. If the angle field has a non-zero value, we need to know the coordinates of the four corners. The tail is represented as a circle, so we only need to know its position. I will discuss the code that calculates the tag position. This line of code paints the tail, while the following three lines of code build the head and the eyes. I will discuss the build shape function soon. The type of the head and eyes is shape. These are constants defined in the consts.rs file. The constant body is an array of the coordinates of the head corners, relative to the head position. We rotate the head by an angle specified by the field angle around the head position to obtain the new corner positions. Then, a translation is applied to get the final corner positions. The monster's eyes are represented as two squares. The constant, I1, is an array of coordinates representing the eye's corners, relative to the head position. Let's explore how the build shape function operates. For each point in the array, we apply rotation, add translation, and then store the new point in a vector. Using this vector and other parameters, we can create a shape object and return it. Now, let's modify the update method to move the food objects. This part of the code is crucial for the game. Currently, the code only handles the motion of the worm, including the boundary behavior. By adding these three lines of code, we can move the foods horizontally. Before we compile the program, we need to make some minor modifications to the createFoods method implemented for the struct game. We need to add a few methods to the food struct. Please pause the video to examine the methods setID, setPosition, and setTag. Now, let's focus on the wagTail method. The tail's position is determined by the head position and orientation. If the food object is a monster, the tail will sway from side to side over time. The variable delta represents the position of the tail relative to the center position. Adding this relative position gives us the final tail position. Finally, we must specify the code path in the cargo.toml file. Let's run the application.
Llama.
Let's move on to the second topic. This is the code controlling the behaviors of the worm and the foods. We have implemented a function to make the foods avoid each other. This function takes two integers, I and j, as the indices of two food objects. It calculates the distance between the two food objects and triggers an avoiding response if the distance is smaller than a certain value. The function also calculates the orientation of the vectors from food j to food I, angle 1, and from food I to food j, angle 0. It then modifies the angle of food I by adding a small value to make it closer to angle 1, and does the same for food j. Now, let's run the application.
Llama.
Now, let's discuss the third topic. This is the method for detecting collisions between the worm and food objects. We will modify the code to introduce an escape response. If the distance between the worm and a food object is far, no action will be taken. However, if the distance is close, we will change the direction of the food object to move away from the direction in which the worm is moving. There is still room for improvement, but for now, we will stick to the current code. Let's run the application.
Llama.
Let's discuss the fourth topic. We have implemented a method called catchWorm. Here, POS represents the position of a body part of the worm used for collision detection. The loop is designed to identify food objects colliding with the specified body part of the worm, iterating only over monsters. If no collision is detected, the current monster is skipped. When a monster catches the worm, the last unit is lost, and the monster acquires the letter of that unit, adjusting the sequence of letters accordingly. This section of the code updates the value of nchars. However, if the number of letter-carrying foods exceeds 3, the last letter is moved to the variable char stack. If the worm does not have any letters and is eaten by a monster, it will die. Let's run the game. Next, we will implement chasing behavior for the monsters. When the worm is within a certain distance of a monster, the monster will start chasing the worm. The code section highlighted by the yellow bar should remain unchanged. We can remove the if statement. Instead, we will calculate the distance between the monster and the last unit of the worm. If the distance is greater than a specified threshold, no action is taken. If the distance is within the threshold but greater than the collision value, the monster will adjust its direction towards the worm. Let's run the application. Please check my GitHub page for the source code. Thanks for watching.